Hello, everyone. My name is Vladislav Sozonyuk, and I'm a senior advisor to the Director General of the Nuclear Energy Agency. Welcome to the webinar series on disruptive technologies for nuclear safety applications. This four-webinar series is hosted by the Nuclear Energy Agency, the Korean Atomic Energy Research Institute, and the Korea Nuclear Society. This is the third event in the series. The first two webinars took place in March. They gave us an overview of emerging nuclear safety technologies and key trends, and set the table for further discussion on safety versus innovations. We have discussed the NI 2050 broad initiative, the effects and possible implementations of disruptive technologies for nuclear safety applications, addressed regulatory viewpoints on safety innovations, and shared the examples and lessons learned from other industries. Today's webinar will be focused on data-driven technologies and their applications to nuclear safety. The experts will share their vision of the potential for artificial intelligence, Internet of Things, and wireless communications. We'll discuss new challenges and opportunities associated with the increased use of digital technologies in the nuclear sector. We'll provide real-world examples of using data innovations to enhance nuclear safety. The series will continue in April and will be dealing with another more specific topic related to nuclear safety in modern environment, cybersecurity. Finally, let me point out that we will be recording each session and we will post the records online in the near future. And now I am very pleased to introduce you the distinguished speaker, William D. Magwood IV, who will make welcoming remarks. Mr. Magwood is the Director General of the Nuclear Energy Agency. Prior to this position, he served as one of the 5 commissioners of the US Nuclear Regulatory Commission. He was also the Director of Nuclear Energy at the US DOE. Mr. Magwood, the floor is yours.
Thank you very much, and welcome to all of you. It's a pleasure to have you join us for today's webinar. As you heard, this is one of a series of webinars that we have organized with our friends at KAERI and the Korean Nuclear Society to examine these disruptive technologies and how they affect the nuclear sector. Certainly, when we first embarked upon the discussion about innovation in the nuclear sector, we recognized that it was going to require a new perspective that needs to be brought into these conversations. Within the nuclear sector, we're very much accustomed to working with ourselves and working with other experts in the nuclear area. But increasingly, as technology evolves, it's clear that the nuclear sector has to look to other industries for input and for technology, particularly, as we will discuss today, digital technologies. Digital technologies are not necessarily the province of nuclear engineers or nuclear researchers, but increasingly the future of nuclear energy will be heavily linked to these types of technologies, to things like robotics, artificial intelligence, machine learning, big data. All these issues will come into play in the nuclear sector. And as we've seen, the COVID crisis, if anything, has accelerated the approach to bring digital technology into everyday life, into industries around the world. And nuclear must be part of that transition, must be part of that evolution. This is a huge opportunity for nuclear, but it's also a challenge because the nuclear sector is different from other industries. We've heard from previous webinars, there are very nuclear specific issues that have to be dealt with as we go forward with this. The price of innovation in the nuclear sector is different from the price of innovation in other sectors. So how do we find the benefits and identify the benefits of implementing these technologies in a way that incentivizes operators and regulators to spend the effort, to spend the resources to bring them into use in the nuclear area? How do we build that confidence? How do we build the trust between the digital technologies and those who operate nuclear power plants? Because the job of those who operate nuclear facilities is to assure safety, reliability as first and foremost. And then only if these technologies enhance those missions will they be successful. So there's a lot of issues to be discussed, and that is the purpose of these webinars, to begin to put our minds around this evolution of technology, to bring in not just experts in the nuclear area, but also experts from other areas to understand how we might evolve in the nuclear sector to accept these new technologies. Because if we were to miss this evolution, this revolution, it's not just an evolution, it's a revolution in digital technology. If the nuclear sector were to be left behind, that would be very damaging to the future of nuclear energy. Young people who are coming out of universities today expect to see these digital technologies used in their everyday lives and expect to see it in the industries they work in. The nuclear sector will not survive if it continues to be in the 19th century in terms of control systems, or at least I should say the early 20th century. So this is very important to us. There will be another webinar coming. There'll be looking at cybersecurity, which is a very important aspect of this. But we hope that these series of webinars that we've produced with our friends in Korea help lay the ground towards this conversation. And ultimately, we hope to welcome many of you to an in-person event, perhaps about a year from now, where we will bring all these issues together in a very comprehensive way. So I hope you find today's discussion of interest. We have some excellent speakers representing different perspectives. And I certainly look forward to seeing the outcomes of this and look forward to working with all of you to push these issues forward. So Vladislav, the floor is back to you.
Thank you very much, Mr. Megot. Now it's my pleasure to invite Mrs. Diane Cameron, who will be the moderator of today's session and will introduce the participants of the panel discussion. Diane Cameron is the head of the Nuclear Technology Development and Economics Division at the Nuclear Energy Agency. In her role at the NEA, she leads an expert team of economists and scientists that support energy policy and nuclear energy policy development among the NEA member countries. Prior to that position, Diane was the director of the Nuclear Energy Division with the Government of Canada. As director, she was responsible for leading and coordinating Canadian public policy on nuclear energy and served as a chair of Canada's Small Modular Reactor Roadmap and Action Plan. Dear Diane, the floor is yours.
Thank you. Thank you, Vladislav. And welcome everyone to our webinar. Welcome to our 4 distinguished panelists who I'll introduce in a moment. Mr. Vincent Champin from Framatome Group, Dr. Ho-Yeon Kang from ETRI, that is the Electronics and Telecommunications Research Institute in Korea, Ms. Dominique Boina from the French Nuclear Safety Authority, and Professor Abhinav Gupta from North Carolina State University. It's my distinct pleasure to be here today to moderate this discussion on disruptive digital technologies and data innovations. Through our discussions today, we hope to gain a better understanding of the status of digital disruptive technologies, those of the greatest interest to the nuclear energy sector, to understand their potential benefits, and to begin to understand the risks and the challenges that they pose. We will hear about the development and implementation of these exciting technological innovations such as digital clones, artificial intelligence, big data, remote monitoring, and the Internet of Things. And we'll hear about the benefits and challenges and lessons learned from the implementation of these technologies in other industrial sectors like the steel sector. And we'll have the opportunity to probe whether and how these technologies and lessons learned could potentially translate to the nuclear energy sector. Without further ado, I'd like to introduce our first panelist. Mr. Vincent Champin is Framatome Group's Chief Digital and Information Technology and a member of the Framatome Executive Committee. Before joining Framatome, Mr. Champin was General Manager for GE Digital Services Europe and Chief Operating Officer of GE France. Prior to these roles, he was with McKinsey & Company, where he led digital and large transformation projects. Mr. Champin has also held several positions in the public service, including notably as Deputy Minister for Policy Planning of Digital Policy Evaluations in France. Welcome, Vincent. The floor is yours.
Thank you. So what I will present today is the potential of database technology and give a few examples about this. So next slide, please. Yeah. So if you look at the typical data approach, you usually in a company, typical company, you have three kinds of data. You have the data that is not digital. That's analog information, that's paper. For example, usual product documentation is in paper. Quality inspection reports usually are either paper or not necessarily structured data. And you also have lots of analog information coming out of analog devices that is not digitized. And so for this kind of data, of course, the first thing to do is to assess the value of where you think you can find improvement for safety or performance, then define a digitalization strategy, and it can take some resources. If you have to digitalize all the paper stock you have, it's quite expensive. And then once you have this data, you need enough time to make the analysis or enough time series to start the analysis. So if you start putting a device that digitalizes analog information, then you come back a few months or years after to have enough data to start making your analysis. That is the first category of data, which is not digital data. Then you have usually data that is digital, but not necessarily recorded, accessible or centralized. Typically, that's data generated by digital equipment, but that is not stored, or customer data that is available, for example, in a nuclear plant, but that the supplier in charge of a machine does not have an access to. And in this case, if you want to get the value, again, you have to define or negotiate an access to the data, and then to have enough data history to start your analysis. And then you have the third part, which is the one on which all the data scientists will think about. First is data that is recorded, fully accessible, clean data. So usually that's data on equipment health, HR, financial data, digitalized documentation. Of course, on this third part, it is easier to get value from the data. The difficulty you have in most companies, and especially in the nuclear, is that 90% of your data is either not digital or not accessible. And the share of your data that is really accessible or shareable across the supply chain to get additional performance and safety is very, very limited. So the first challenge is, of course, to reduce the part of not digital data and extend the part of the data that is available to do some data science. It might look obvious, but in most companies, when you hire data scientists, you start working on this issue, then you're stuck into this problem that most of your data need some cleaning, need to some storage, need to be digitalized before you get any value out of it. Then next slide, please. Then, of course, when you have the data, in fact, you have 6 ways to get additional safety and performance with it. So the first one is through compliance, so ensuring that you manage your data according to the rule. So I will go less on this one, but it's very important that the first thing you expect from your data is not creating you additional problems. Then we have what we call business intelligence. Business intelligence is about making not very sophisticated analysis. Is most helping operators or managers to see their own data in a very simple way. Then you have what we call automation. Automation is using robotic processes, things like macros that process your data in an automated way. So that's not complex, that's not high-level science, but that's what you do, for example, when you want to automate alerts, when you want to automate training processes or processes to ensure that the people that do a certain action have the right qualification. It's not smart, but you can automate a lot of things. And this is, of course, one key way to create value out of your data. Then you have what we call domain science. So domain science is basically applying data science using physics or high-level knowledge of material behavior. So that's typically what we do when we do, for example, resistance studies for nuclear equipment. Then the next step is applied mathematics. So typically predictive maintenance, identifying patterns in your machine data that can lead to security issue or performance issue. And then you have machine learning. So machine learning is not mathematics in the terms that you apply or build your same model, but it's leveraging software components that can automate, find patterns in your data. And basically extracting value, being more efficient, more safer based on data is using the 6 levers on the different forms of data I presented in the slide before. Next slide, please. So the question is, what are the typical challenges? So for the data access, typically the challenge is nuclear, is you have limited connectivity and usually strong barriers to data exchange between operators, equipment maintainers, and service companies. The second issue you have is data sharing across supply chain. In most cases, safety issue or safety will appear either on one specific part of the supply chain or will involve different partners. And of course, if this partner can't share the same data, then you are limited in your ability to extract additional safety from your data. The third issue is access to massive computation power. So now the norm outside nuclear is, of course, to leverage cloud solutions. So you don't have to own massive computing power if you want to do, for example, massive artificial intelligence on consumer data in a commercial website. For the nuclear, the challenge is that usually your data is classified, and for sovereignty reasons, you will be limited or forbidden to use this standard for high-level computation. So you will need a more expensive way to use computing power, which might be having your own data centers, your own computation capabilities, or working with specific sovereign solutions which are more expensive and which, of course, offer less leverage that we'll find in other industries. The next issue is to have access to ready-to-use software components. Again, if you want to do face recognition, pattern recognition on consumer data, that's very easy. You use ready-to-use software components that are proposed by the most well-known vendors on the place. And in a few hours, you can develop a working web application. In the nuclear, you have 2 challenges. First one is, again, this sovereignty challenge. You can't necessarily send your data to a public cloud, so you will be limited in using the software components that are related to this cloud. And the second issue is you have cases which are very, very specific, identifying cracks or issues in fuel assemblies. You will find no on-the-shelf software components that will do the job for you. So you need to invest more. You will need to be more in the software editor role and not just using a ready-to-use software component that any non-sophisticated developer could use in a couple of hours. And the last point is about cybersecurity, of course. Again, when you use standard components and methods, you make the assumption that the standard security levels that are protecting you are good enough for you. When you are in the nuclear industry, you know that you will need an additional level of security, and you can't necessarily rely on the market standard. So you will need to invest more time in architecture, in validating solution, and in ensuring that the specific case on which you want to use the standard software component are authorized by the regulation, authorized by the sovereignty rules that forbid you from exposing sensitive data. Next slide, please. Now for a couple of examples that works. So the first one is sharing the same data on the nuclear equipment from design to installation, to service, and to decommissioning. So that's what is about. It is about managing the full life cycle of an equipment and sharing the same data from designers to builders to operators and to the people in charge of commissioning. And in fact, there are lots of gains to get both on safety and performance, because the level of expectation of requirements you usually put on a nuclear equipment is very, very high. So sharing the same data gives you many ways to automate the way you ensure the requirements are met, and also for the regulators to automate ways to ensure and to check that the proof brought to you that the equipment is compliant are good enough. So this one is probably by far the first case of getting data with additional safety with more data, because basically the requirements are so complex that you need a machine to ensure that they are all met. To give you an example, if in a typical steam generator, the rapport de fin de fabrication, so the report you make with all the requirements and all the proof that shows you met the requirement, makes 13 times the longest novel in the French literature. So La Recherche du temps perdu by Proust, you multiply this by 13, and this is the volume of data you have to provide to show that your equipment is compliant with the requirement. So of course, with data and digital, you can do much better than with just paper. Next slide, please. Second example is about training. So this example, it is an example that we did to automate and to give new tools for the training for the people in charge of sorting the pellet and making quality control on the fuel pellets. So basically their job is to ensure that you have no defective pellets, you have no cracks, you have no abnormal shapes, and it takes a lot of time for the operator to be trained. And usually they are trained by coming to the plant, which also causes some additional risks. And what we did is a simulator that generates 3D photorealistic pellets with all the kind of defects and some non-expected defects that helps operator to train in a very safe mode, and also to accelerate their training, because you can generate any possible form of defect and also test the operators very, very easily. And to do this, you are not forced to put them in a place where you manipulate radioactive matters. So this is a good example where data digital help ensuring safety and performance in the same time. And in this domain, I'll come back to it. This is a domain where we could go much further, because, for example, for legal trainings, in many cases, there are still regulations that do not authorize this kind of trainings, even if they are more effective. And in fact, we did tests that show that people remember this kind of training sometimes better than the typical classroom trainings. Next slide, please. So maybe I'll skip this one because I'm a bit late. Next slide, please. So the key message, and then of course I'm open to questions. So first message is there are still lots to do with very specific challenge in digital. So the potential for better performance and security is really high, and it's really a priority to push and to ensure that this solution can develop much more going forward. Second thing is the highest potential is when you have a mix of digital and industrial methods. What I showed you with the first life cycle example is in fact an example that leverage both standardization, system engineering, lean methods, and digital tools. And the best improvement come where you mix performance methods and digital. Third message is there is a strong and structuring role for regulation. Of course, if regulator ask or force you to bring paper, then you will be slowed in your process digitalization. To the contrary, if digital matters is either authorized or compulsory, then you will push the whole supply chain to digitalize itself, and it will bring you additional safety and additional performance as a side benefit. And second remark is there's still a lot of potential for digital training, and this potential still need to be unlocked. And the last remark, but probably the other participant will come back on this, this is no magic or is it tax? So digital transformation takes time. If you look at industrial domain, in many domains, they are just in the first phases of the transformation, and nuclear is probably lagging a little bit. And if you think about this, think also that the internet bubble was 21 years ago. So yes, it takes time. It takes 1 or 2 generations. And you need also to have a realistic level of expectation and to be totally confident that we will bring huge benefit, but you need time, method, and resources for this. Thanks a lot for your attention.
Thank you, Mr. Chaffin. I think what we'll do is we will invite the 4 presentations in a row, and then we will have a good discussion with Q&A all together at the end. So now I'd like to turn to Mr. Ho-Young Kang from ETRI. He is Principal Research Scientist at the Electronics and Telecommunications Research Institution, that is ETRI in Korea. During his career, Mr. Kang has focused on developing high reliability, real-time wireless communication technology, network solutions for extremely harsh industrial sites, and Internet of Things-based emergency detection and radiation management systems for decommissioning of nuclear power plants. Dear Ho-Young, the floor is yours.
This is Ho-Young Kang. The presentation title is Industrial MCMH IoT Network Technology. MCMH means multi-hop, multi-channel, and multi-hop. Okay, next slide. As for the IoT coverage issue, the instruction of LPWA technology made it possible to service up to 10 kilometers. As you can see in the picture, high-speed IoT service use UWB or Wi-Fi based technology, but the low-speed IoT data service used Zigbee or Bluetooth in the past, but the transmission distance was too short, make it difficult to use universally for IoT application. Recently, LPWA and multi-hop IoT network technologies have been developed for the low-speed IoT, enabling low-speed wide area IoT service. It is difficult to use LPWA technology in application where high reliability transmission and low latency characteristics are important, such as factories or smart city, etc. Therefore, a multi-channel IoT network technology capable of providing high reliability and low latency transmission characteristic may be a new alternative. Next slide. I will explain the wireless network technology background and requirement to support the commissioned nuclear power plant IoT service. In order to monitor the safety of workers for nuclear dismantling work, the mobility of communication node and the following should be supported. First, when installing a large-scale IoT node, network configuration and operation must be supported. Second, wireless communication technology using unlicensed band is required. And multi-hop technology is required to resolve the radio shaded area and expand the network. And installation and maintenance should be easy, or network stability is required. Finally, reliable data transmission and reception in wireless section is required even in poor radio wave environment. And to meet these requirements, high reliability, low power, low latency, industrial IoT communication technology with mobility is required. Based on the IEEE HR2.15.4 DSME MAC standard technology, we will introduce Starlink IoT communication technology suitable for applying nuclear power plant to IoT service by adding mobility, self-network organization, and multi-hub OTA technology. Next slide. ATRI developed the DSME MAC standard IEEE HR2.15.4 enhancement standard for the industrial IoT service. So ATRI has the core technology for the DSME MAC. The DSME MAC standard has three main features as follows: high reliability and data transmission delay guaranteed support. So the high low power performance. The main target service is smart factory automation, plant process monitoring, and other industrial IoT service. Next slide. This figure shows the application structure of Starlink IoT technology. In order to cover a wide area in a large factory area or in a complex power plant interior, and to satisfy the low latency characteristics, 4 IoT access points were connected by clustering. Each IoT sense can be connected to an IoT node in a multi-hub and mesh network structure. The detailed figures and specification of Starlink will be described in detail in the next slide. Next slide. Yeah. IoT network technology was developed based on the IEEE HR2.15.4 and K international standard technology, which has the following main features. First, improving radio link reliability using multi-channel and retransmission technology. Second, support for the mobility and definite delay data transmission. Third, support automatic configuration of network technology suitable for industrial site and minimization of radio wave interference. Final, support OTA. OTA means over-the-air program update function. Yeah. It has a main advantage in a poor industrial IoT wireless network system composed of large-scale dense nodes, and it is possible to configure a one-hop extended network or mesh network. Next slide. And Starlink is capable of providing timely transmission and low power characteristic by applying a multi-hop synchronous TDMA structure and high reliability transmission by applying channel diversity. In addition, it is possible to minimize the shaded area by providing multi-hop IoT network. It supports mobility required by industries such as nuclear power plant. Next slide. I will explain the high reliability technology. First, improved transmission reliability in wireless section by avoiding interference channel based on multi-channel. So our multi-channel is transmit and receive by channel hopping in all time slot using a number of predetermined channel hopping list values. Second, enhancement of transmission reliability through redundancy of network paths. So the network management server retransmit data through the bypass route, even if data is lost in the middle of data transmission, by allocating additional resources for the corresponding route when recasting a bypass route when allocating resources. Third, by using the media access control method of TDMA method for data transmission contention, and collision are prevented, which are a problem when operating a large-scale network. Next page. And next is mobility support technology. This mobility procedure is as follows. Mobility node predictably receive beacon signal around them, tracking the existing beacon signal and the new beacon signal at the same time. And this figure shows the moving workers in the dismantling work. So the work moved to the another region. Our network detect the mobility handoff and handoff function. Next page. I will explain the auto configuration function for the IoT network topology. In the first, when installing the system in the field, an experienced network engineer designed an IoT network topology through a long link test and installed the network, which took a lot of cost and time. In order to improve this, it is a function that automatically creates an optimized IoT network topology by using the surrounding information for all nodes when a field manager without expertise freely places a node at a desired location. The function proceeds as follows. First, when the system is started, all node collect channel and neighboring node information and send it to the server. The server transmits the available channel and clustering information to the node based on information of all nodes on the network and configured clustering evenly in consideration of load balancing. So the server allocates time slot resources for each route based on the network topology and informs all nodes. All nodes periodically transmit data based on the allocated time slot information. Next page. The following describes the over-the-air downloading technology among the Starlink IoT technologies. As a wireless downloading technology for updating large-scale network, the uplink and downlink structure according to the system mode is dynamically changed and operated so that The scalability is excellent according to the network size and topology shape. In particular, it has the characteristic that the server processes the entire network firmware update at once by using differentiated multi-hop OTA technology. Next page. This is main feature of our IoT network comparison. It is the picture of long distance low rate wireless transmission in 900 MHz band, international standard based technology, and strong against the channel interference by using multi-channel. Excellent coverage expandability by supporting the multi-hop network, and easy system installation and management is major features. Next page. This through a large-scale cluster node-based IoT network verification test, the function and performance of Starlink IoT network were verified. The system configuration is as follows. Number of nodes, 192 nodes. Number of access point, 3 access point, and server and dashboard, 1 unit. And maximum topology depth is 3 hop. The system procedure is follows. Analyze channel and node information and transmit it to the server. The server collects the information from all nodes and performs functions such as creating a clustering topology and automatically allocating resource. All nodes of network transmit and receive data based on the allocated resource. Yeah. Next page. This is a nuclear power dismantling management technology applying Starlink IoT network technology, mobility and multi-hop high reliability industrial IoT network that can perform real-time location recognition of mobile workers and dosimeter measurement, data collection, and autonomous driving radiation measurement, robot data collection, and fixed radiation measurement data collection should be supported. Okay. Next. Okay, this is POSCO application. POSCO Gwangyang Steel Works space is very wide, maybe 6 kilometers by 6 kilometers. So we installed the partial discharge monitoring of very high voltage cable connection, but connection distance is above 1 kilometer and 6 cents per node. And this figure configuration for the high voltage cable connection monitoring service. We already installed and verified in the last year. Okay. this is also the POSCO, the steel works. The application serves installation and verification in Pohang Steelworks, the IoT facility monitoring for health monitoring of large motor, and monitoring of oxygen density in combined area, and temperature monitoring of steel making rolling facilities. We also installed and verified in the last year also. Okay, that's it. Thank you very much.
Thank you, Dr. Kang. A very interesting presentation, especially on the application of Internet of Things to nuclear decommissioning and other nuclear tasks. I'd like to turn now, please, to Ms. Dominique Boina. I'd like to introduce Ms. Dominique Boina from the French Nuclear Safety Authority, ASN. Since July 2018, Ms. Boina has headed up the initiative at ASN to apply artificial intelligence to mine data coming from inspection letters and incident reports. She has held a variety of positions at ASN since 2007, including project manager, safety and radio protection inspector. Prior to joining ASN in 2007, she worked in the private sector in engineering, in quality assurance, and manufacturing. She is a black belt project manager. Welcome, Dominique. The floor is yours.
Hello to everyone. I'm very glad to make this presentation. And I thank Vladislav for the introduction and the organization for this webinar. I will focus this presentation on science, which is the first AI project led by the ASN. Next, please. ASN is the French nuclear safety regulator. On behalf of the state, we ensure the oversight of nuclear safety and radiation protection in order to protect people and the environment. It informs the public, decides and acts with rigor and discernment. Its aim is to exercise an oversight that is recognized by citizens and regarded internationally as a benchmark for good practices. ASN, this is more than 300 inspectors for 1,500 inspections per year in order to control 58 reactors, 85 nuclear cycle installations, and more than 50,000 medical and industrial use of ionizing radiation. It corresponds to more than 10 million points control points. Next, please. Due to its transparency policy, ASN puts on in internet site since 2002 all the letters that has been written after any inspection. It contains all the gaps seen by the ASN during the inspection. The median of pages of these letters is 4 pages. These documents contain up to more than 200 technical information. These letters are yearly analyzed, but it is difficult to make it on several years, taking into account the mass of data. In order to illustrate this purpose, I have put one example of paragraph of a letter written after an inspection dedicated to seismic hazard. And you can see that it refers to 6 key topics related to material or organization issue. You can imagine that it is difficult to know by advance what you will find into these letters. Therefore, we have decided to use AI to exploit all this data. Next, please. Imagine that you are an inspector. You have to prepare an inspection on one NPP, for example, on the topic related to seismic hazard. What was the former findings? Do I have trends, weak signals, repetitive gaps, or good practices? Is there controls not done for a long time? So Science is going to help you. Next, please. Thanks to Science now, inspectors have access to in real time to letters starting with a word or an interesting topic. The timeline helps them to concentrate on a specific period, site, licensee, or level, because in fact, in France, we have the same design for all NPPs. All this data can be exported into an Excel spreadsheet. Next, please. We have also designed graphical representation. On the left, the map allows to compare the number of findings regarding the number of opportunities. So I mean the number of installations. On the right, the graphs compares for each system or circuit the number of findings and the number of events declared by the licensee on the installation. Next, please. Science is related to the whole inspection process and emergency situation process. Our ambition is to mobilize information in real time and get warnings on trend or wake signals. For the preparation, inspectors have access to findings observed during former inspection on the installation or similar installation. It helps them to identify the most efficient points to control, and it gives also inputs to the technical directions to update the inspection guide. When they write the letter after the inspection, inspectors have now access to similar findings. The evaluation coming from the inspection are done in real time. Science gives also trends and can early identify generic issues in order to define national actions with the licensee or suppliers. This data aggregation allows to improve the inspection program with taking into account the result of the inspection in real time. It gives the opportunity to take into account qualitative data and not only quantitative data in order to build the inspection program. Finally, during emergency situation, ASN has access to a site or material assessment in real time. Next, please. Next. In order to develop this machine learning tool, we have first to clean up the data. We have developed a specific tool for labeling, and we bought a computer with high capacity of calculation and video card. The AI algorithm has been developed using BERT and SPACY. The third output is an API based on Elasticsearch, which is fed by metadata and installation database. The new letters are treated every night and are available in the tool the day after publication. The metrics are calculating, taking into account also the events declared by the licenses. Next, please. The labeling has been a crucial step because we had to develop an ontology dedicated to our activities. We wanted a tool able to allocate a sentence or a word to several classes. And finally, the labeling needed to mobilize a lot of people in order to label a huge quantity of letters. Regarding the ontology, the goal was to define a classification that should cover all the domains, taking into account these constraints. We want to get a fine analysis and not to have too many classes because we want to have enough data to get a good learning phase. The classification covers twice topics like 5M fishbone and technical topics, which are specific to each main domain covered by the ISN. NPPs, nuclear fuel activities, radio protection, and transportation. 4,000 letters have been labeled by more than 300 inspectors. The gauge has been calculated in order to be confident on the quality of the result. Next, please. In order to measure the success of the project, we have put in place quantitative and qualitative metrics. For example, we have dashboards to follow the use of the tool, which are calculated, and we launch specific surveys with users. Next. This project is a success. In order to complete, we have put in place a dynamic project team involving inspectors and IE teams. More than 300 inspectors, as I said before, have been involved. It has been possible because the top management of the ASN was fully involved and allowed especially to spend time on labeling, user research, and risk analysis. Not all the people were open to new IT technology. This project has been successful because we have spent time to convince And it was essential to lead this kind of project now, even if we did not know at the beginning if it would be successful. Next, please. In conclusion, science contributes to improve the control policy of the ISN. I mean, go ahead to more efficiency and focus the control on actions that produce the most benefit for safety and protection of workers, patients, public, and environment. I thank you for your attention.
Thank you, Ms. Buena. And now for our fourth panelist, I'd like to introduce Professor Abhinav Gupta from North Carolina State University. Professor Gupta is director of the Center for Nuclear Energy Facilities and Structures and professor of structural engineering and mechanics. Presently, he is also serving as the president of the International Association of Structural Mechanics in Reactor Technology. His research interests are focused on uncertainty quantification, probabilistic risk assessment for external hazards. He has worked on developing new computational and probabilistic models for decision support and strategy development for reducing the operation, maintenance, and construction costs associated with structures, systems, and components. Welcome, Abhinav, the floor is yours.
Thank you, Diane. Good morning, everyone, because I'm here in the United States. Some of you, it's good afternoon and good evening, depending on where you are located. What I'm going to talk about is some of the data-driven innovations and some of the related work that we here at North Carolina State University have been involved with. And what I'm going to talk about is specifically two projects, which are currently ongoing projects at our center. And our center is called Center for Nuclear Energy Facilities and Structures. So a little bit before I get into the two projects, and I promise you I'll keep it very short as I have only 3 slides for each project. So let's go to the next slide, please. Before we get into the projects themselves, a little bit about who we are. We are a university, industry, government consortium at a university, and that research at our center is sponsored by several industries around the world. From Europe, we have giants like EDF. From Asia, we have giants like KHNP and KAERI. In South Korea and in the US, we have Dominion and Duke, which are a couple of biggest nuclear utilities in the world. The research at the center is can be kind of divided into 3 different parts. One is the sustainability of the existing nuclear reactors and the existing fleet of reactors, and helping them with operation, regulation, ongoing license renewals. We also have research on improving the resiliency and also conducting civil accident management for the nuclear fleet. And then we are working on these digital transformations, which we are using to help reduce the cost of building new plants and facilitate the growth of nuclear energy. So with that background, let's get going talking about some technical work here. Next slide, please. So the first project I'm going to talk about is called Nearly Autonomous Management and Control. Its acronym is NAMAC. Both these projects that I'm going to talk about are sponsored by Department of Energy in the United States, an agency of DOE called ARPA-E, Advanced Research Program Agency for Energy. In particular, NAMAC, it's a multi-university national lab industry partnership. So multiple universities other than NC State, even though we are the lead, we have New Mexico State and Ohio State as part of this team. We have Oak Ridge National Lab, Idaho National Lab that are part of the team. We have industry members like Zachary, which are integral part of the development work, and we have TerraPower with the advanced reactor that are part of this team. So in this project, this slide essentially summarizes what we are trying to do. What you see on the right-hand side are 2 figures. On the top is what we call as a current focus of operating a nuclear reactor, where much of the decisions lie with the operators. We have sensor data or whatever data we are collecting. We get that data, and the operators are responsible for diagnosing if there is a problem, making predictions, and then taking decisions on what actions are needed. What we are proposing is in the bottom right corner here, and this is the work that we are doing, and we have been working on it for more than a couple of years now, and we have achieved very good success. We are proposing this NAMAC, which is an artificial intelligence-driven, machine learning-driven system, which will help the operator. It's not a completely autonomous system as one may imagine, but think about an operator. Based on the operator guidelines, it can only be trained, operators can only be trained for very small set of instructions or possibilities or scenarios. Whereas NAMAC can use the power of computing, AI, machine learning, digital twin technology, which is really the engine behind it, and churn out hundreds and thousands of scenarios whenever something is deviating the normal operational situation. And it can provide operator with a whole set of possibilities, both in diagnosis and prognosis of what can be done. And in fact, provide even a ranked list of options of what the operator should do. And the real decision lies with the operator on which particular option to go with or whatever decision to be made. But then, irrespective of what decision is made, NAMAC then again tracks the performance of the plant. And as the situation evolves, NAMAC can track and see if the plant is following the same path as it was assumed by taking a certain action. And if it is not, that means that action was not appropriate and a new set of actions will need to be taken. So all of that help for the operator can be provided by NAMAC. It really is disruptive in the sense that it has the potential to change the entire risk profile of the plant. And what it does is it changes the operation of the plant from what we call as operator-centric to NAMAC-enabled for this nearly autonomous management and control. The real engine behind this is a digital twin technology. And I'll talk about that in a minute as to what that is. But what NAMAC truly is doing is it is projecting the consequences of an action taken by the operator into the future. And then even accounts for uncertainties, because we will always have uncertainties. And so the decisions have to be made in the context of uncertainties. And then it continues to track the progress of plants' performance, behavior, and see if newer actions need to be taken. Next slide, please. So what is a digital twin? Well, it's easy said than done. A digital twin is like a digital replica of the plant, which is not, many people tend to think of as a large simulation model. That's exactly what it is not. What it does is a digital twin actually collects a lot of information from sensors, any past experimental data that is available, either laboratory data, field data. It is built on the knowledge from advanced simulations in many different scenarios which we don't have actual experience with. It takes prior knowledge to the extent that we can, and it's available. Uncertainty, as I mentioned earlier, and even the expert knowledge. And then it creates a digital replica which would be able to age with the plant as time passes by. So it should be able to continuously update itself based on the data being collected, and then continue to age with the systems and components of the plant. Next slide, please. So we have a very successful implementation of digital twin for the advanced reactors. And what we based our study on is, well, we don't have an actual advanced reactor today. So what we did was we used EBR2, which was a research reactor built in Idaho National Lab. It was a liquid sodium reactor. And there's data available from that reactor as well as operating procedures and operators manuals. So we have used all of that to develop this implementation for our digital twin. What we have here is what we have implemented and published, that this is a 3-layer architecture. The bottom layer is called the knowledge base, which is basically embodies the knowledge that we have to train the digital twin. And that training goes in the second layer, which is called the development layer. So we use whatever the issue space is, we define the behavior of plant into different scenarios, different scenario-based models, and use simulation tools, data repositories to kind of train these digital twins. And what we have is not a single digital twin, but a hub of digital twins, meaning different digital twins for diagnosis, different for prognosis, different for strategy assessment. And even within that, there are all suite of different algorithms which work better for different conditions, different scenarios. And then the last layer, the top layer, is really the operational layer, where the digital twin, which has been trained, is then integrated with the sensor data, and it continues to feed back and train the digital twin, but also make decisions in real time. Next slide, please. So that was about our NAMAC system. The next 3 slides talk about another project, which is also sponsored by ARPA-E. And this is being done in conjunction with Idaho National Lab is our partner in this, because Idaho National Lab is right now designing a versatile test reactor, VTR. And they have some other labs that are being constructed. And this project is on using digital technology, digital transformation in the area of construction and construction management. And in particular, we are using virtual reality and augmented reality platforms to be able to build this thing and manage the modular construction aspect and offsite manufacturing in a very, very modern looking, innovative way. What it shows, this figure is on the left-hand side, if you see the circle, we have a project site. We can use reality capture technologies like video captures, laser scans through drones, robotic arms, unmanned vehicles that can go through the site and create 3D models of as-built systems. And then compare them with BIM. BIM is what we call as building information models. These are 3D models that are used to drive the construction at the site and even simulate the construction progress. So what we get from the reality capture is real time progress and 3D model of as-built system, which can then be mapped into the BIM models. And one can use digital concepts then to automatically evaluate whether our as-built systems match what were as designed. On the right-hand side, we see an offsite manufacturing facility or hundreds of them around the globe, which will be the vendors. We can do the same thing for smaller parts of any component, any system that is being manufactured or modular construction. And then before we ship that, it can be virtually brought into the site and then see if it, for example, fits the site or not, or it multiple components being manufactured different places in different geographical locations. Do they fit together? If they don't, there's no point to ship them. So next slide, please. This slide shows exactly what I mentioned about virtually fitting things together. On the left-hand side, what you see is a green colored piping part, which is manufactured at an offsite. And what you see is one of our graduate students putting on his virtual reality headset. With that, he can actually pick up this part and try to fit it into the exactly as-built scans of this construction site. And he's trying to fit it, and if it fits, it's perfectly okay to ship this particular part. What you see on the right-hand side is actually the same thing, but being now done even more automated way, where we can kind of get these things to fit together and even see whether all the specifications, tolerances are satisfied. And in fact, there is no need for actual measurements because one can do digital measurements. So physical measurements for inspections or actual real inspections are not really needed. One can do this digitally, and that saves a lot of time and approvals, and also transparency on which manufacturer went bad in getting this whole thing assembled. Next slide, please. So the last slide here for me essentially talks about a summary of what we are doing in this as-built models using reality capture. We're using a lot of different technologies like the unmanned vehicles, drones, robotic arms, with cameras, laser scanners to get the visual data and put these 3D models together. We're also using thermal imaging, high-speed cameras, which can do very localized monitoring for loads and quality. And all of this can come together to actually now go back and integrate with our digital twin work, where we can build what is called as-built digital twins. And so that will really help going forward if we have digital twins, which essentially are not as designed, but rely on as-built information. So that's all I have. Next slide, please. And thank you. I appreciate the time.
Thank you, Professor Gupta. That was a fantastic overview of what you're doing at North Carolina State University in this area. I'd like to invite all 4 panelists to please turn their cameras back on. We have run a little bit behind schedule, but we still have a little over 15 minutes for some discussion and some Q&A. So I'd like to start actually by just reflecting a little bit on some of the themes that cut across the 4 presentations that you provided today. Certainly the potential benefits of digital disruptive technology innovation are exciting and apparent. With new functionality, new insights, greater visibility into plants through the possible application of Internet of Things, reducing human exposure, changing the risk profile of NPPs with the application of these technologies, to ultimately drive improvements to efficiency and safety. These are admirable objectives and really exciting possible benefits. But we certainly also heard about some of the unique challenges in applying these to the nuclear sector, from very real physical challenges like operating in a harsh radiological environment, but also sort of some security challenges, right? So we heard about the fact that these innovations cost more to the nuclear sector compared to other sectors for a variety of reasons. Limitations on the ability to buy off-the-shelf software, limitations on the ability to use the cloud and open source, that need for sovereign control of data management. So these higher costs limit, perhaps to some extent, the ability of the nuclear sector to implement and realize the benefits of these digital and data innovations. So what I'd like to first ask is about the challenges and the recommendations you may have for overcoming these risks and driving down the costs potentially. So if you had to name sort of the number 1 challenge and maybe make a recommendation to I think that we heard that there's a role for a range of actors, from the supply chain for sharing data, the operators, policymakers. Certainly there's a role for regulators to prepare. So that's sort of the overarching question, but maybe I'll target a specific question to each of you. Dr. Kang, perhaps you could go first. From a researcher's perspective, do you have a recommendation for whether it's operators or policymakers or regulators? What can they do to incentivize and support R&D and support successful deployment of the technologies that you are working on?
Yeah, in the existing wire-oriented firefighting field, there are more and more cases of introducing wires together. This complements the advantages and disadvantages of wired and wireless. And wired communication is likely to become useless in an emergency. And only wireless communication operated with a battery and low power may be operated. Therefore, the government need institutional support so that IoT wireless communication can be used in combination with wire communication in nuclear power plant field. This is because in the case of Fukushima nuclear power plant accident, there is no way to know the internal situation of nuclear power plant when the power is turned off. If wired and wireless are built together, it is much easier to understand the situation inside the nuclear power plant and control facilities, even in extreme emergency situations. Okay.
Thank you. So what you're describing is a role for the state or governments to play in establishing a sort of infrastructure to support this deployment. Did I understand correctly?
Yeah, the government and nuclear power plant that dislike wireless.
Thank you.
That's a major problem.
Thank you. So there's a role for
Okay.
governments. Okay, let's turn to you talked a lot about data culture, and it raised for me a question of whether or not the aggregation of data itself creates new risks and how to mitigate those risks. I'd also like to ask you about the role of the regulator and how the regulator can prepare for these new technologies and also for overseeing the new risks that are introduced by the aggregation of data itself. How, as a regulator, do you build up the right capacities within your teams in order to be future ready, in order to be future proof within your organization, to be ready to deal with innovation?
Yeah, we are building and operating in the IoT network using currently developed technology in postcoast steel mills in harsh environment and preparing to apply the nuclear power plant decommissioning site. And then we expand our technology to the nuclear power plant inside. Okay.
Thank you, Dr. Kang. Thank you, Dr. Kang. Ms. Buena?
Yeah.
The question was for you. You talked a lot about data culture. You talked about the possible benefits that can be derived through big data and the aggregation of data. It seems to me, though, that the aggregation of data not only gives you new insights, but it also creates new risks. I wondered if you could speak to the role of the regulator in helping to mitigate those risks, and also how the regulator can prepare and build the right capacities to be able to be future-proof, to be ready to regulate innovation.
So at any time there are changes that both the industry and regulators must adapt in order to remain globally recognized. The 19th saw the emergence of the systematic use and widespread use of computers. At the beginning of the last century, it corresponds to the time when the data was stored in applications dedicated to a function and therefore disjointed, requiring manual but not systematic cross-references. We are now aware of the importance of the stored data, but there is still a lot of work, like Vincent Champagne said, to be done on how to exploit this mass of data. New technologies allows us today to exploit data, especially textual data, which were not exploitable 5 or 10 years ago. Like any change, the one that concerns us today, which is described as disruptive, but which the previous ones were also, requires an adaptation. Risks are new, however, governing by data means mastering it and requires to rely on reliable data and always remain questioning. Data quality is a key importance. You have to make sure that models are accurate. For this, you need to have a large number of reports. The second point is how we came to the decision. It is essential to understand how it has been produced from a safety perspective, and it is really important to have it. And we have to be safety focused. Finally, we should not lose the sight of human. This is really important. And I would like to add that the new tools have to suit with the current processes. Nevertheless, like any change, the implementation of these disruptive technologies have to involve the management, use the risk approach, and put the users at the center of the project management. These new technologies need to have specific knowledge into data science, but not only user researcher and expert in agile method, for example. To conclude, these new technologies will make emerge also new use of data, new management of organization, and new practices that we could not imagine at the beginning. And the result is not time profit. This is also quality profit, in my opinion.
Thank you. Thank you. Very interesting. I'd like to turn, I have a question following up on this, this theme of data culture that was woven throughout Ms. Buonan's remarks, but also Mr. Champagne, you also spoke quite a bit about data culture. And you spoke about the need for training, but I want to ask you whether it is just a question of training, or is there a culture shift implied by this new concept of data culture? Are there any similarities between when we talk about safety culture and now that you've introduced this concept of data culture? Is this a bigger change management challenge than simply training?
Thank you. Yes, so it is a challenge, but it is a challenge for everybody. And I would say every big disruptive technology. If you take, for example, the steam machine, there were 50 years between the first prototypes and the time where really a steam machine started replaces horses. And as I mentioned, the internet bubble was 21 years ago. So the children who were born at that time are now working on our project. So it takes time. And I think it's also a question of technology maturity. So, for example, if you think about the car industry, to use an early car, you really need to know a lot about mechanics because it broke all the time and the road was not necessarily meant to use these cars. Now, with time today, even the service people don't know how a car works. They just replace an electronic card because the technology is very, very mature. For digital, you have some technology we are now relatively mature, how you use a computer, how you can develop an application on premise. Some which are mature for industry, which have, I would say, low standards for security. So the cloud is relatively mature for them. And others are still, I would say, not totally mature in the domain where there are lots of security concerns. We had an example of an IoT network system. You have lots of plants where the plant operator just forbid any connectivity whatsoever unless they install themselves. So in this specific case, you can have a working technology, but you can't get the benefit because of maturity of the whole ecosystem. So I think it's much stronger than just thinking, okay, there is a working technology like car, people have car driving lesson and then everything works. It's a mix of course, being much more open with this technology, and with generation, with time, it will change. I think they need, I would say, some relatively voluntary attitude from the regulator, and it could be more voluntary. And I think the iteration between regulator and regulated could be more dynamic. And I think the NEA could be a good place to have some part of this dialogue. And there are also industry efforts to create standards adapted to the nuclear constraints. And on this, we're still very, very far away. Now, when you have all this digital transformation, it's about using the digital toolbox and get performance out of it. So where you come in a system which was designed and meant without digital, and it's the case of most the nuclear plant today, they were designed much before digital, then it's more complicated because you have to deal with legacy technology, and you have to ensure that whenever you transform something analog with something digital, you do not create an additional risk. But with time, I'm 100% confident that this technology brings much more safety, much more performance than the risk. But of course, you have to deal with the risk in a reasonable way. Again, if you think about the cars, if you told people, okay, we'll just stop using cars because it's a technology that kills people, it would be totally crazy, and you will lose lots of benefits. In fact, you would have more deaths because people not able to reach a hospital, people not able to bring medicine to remote places. And with time, today, the risk for cars, you think about FGA, airbags, active technology, driving regulation,
Yes.
speed tickets automated, are such that you take most of the benefits of the technology while reducing a lot the risk. We are not in this state of maturity today, and I think it's our mission, both in the industry and for regulator, to increase this maturity.
Thank you. I think that's an excellent point about the maturity of the whole ecosystem, and it's another way of being one of the themes from your presentation, where you talked about partnerships across the supply chain, across the various owners and source of data, all up and down the supply chain. And I really appreciate now bringing it around to the concept of a whole ecosystem, because that might be one of the places, those types of partnerships, the maturity of the ecosystem, those might be ways to drive down the costs. And certainly I would agree with you on the role of international cooperation and the role that the Nuclear Energy Agency can play in convening some of those collaborations that will build the maturity and build the capacity up and down the supply chain and across the entire ecosystem. I'd like to turn now, we have very little time left. We're almost up against the end of the session, but I would like to direct one question to Professor Gupta. As you were speaking, I really appreciated that when you began your presentation, you situated the discussion about the specific technology innovation within these broader strategic objectives of long-term operations of nuclear power plants, resiliency and severe accident management, and reducing costs, and of course, new build. So you really were talking about different phases of nuclear power plants. And what the question that came to my mind that I wonder if you could address, are there some phases of nuclear power plants that are more ready, whether it's because the costs of introducing innovation would be less, or because the risks would be less or more manageable, are more ready for the introduction of some of these disruptive digital technologies, where that would be an easier entry point for us to establish and become comfortable as a sector with the application of data innovation. So for example, whether it's the decommissioning, or whether it's the design phase, or should we jump right into the middle with operations? Professor Gupta? Oh, I think we have lost. Professor Gupta appears to be frozen. Oh, it's a cliffhanger, folks. I guess I guess we will have to we'll have to wait for our live workshop in 2022 for the answer to this and many more questions. This has been a really fantastic session for starting to surface some of the puts and takes, the possible risks and benefits, and certainly has helped us at the NEA understand the space a little bit better and the complexity of the space, which I think is just going to help us even more when we turn our attention to planning our full in-person workshop in 2022. So I'd like to thank all 4 panelists for really stimulating, interesting descriptions and discussion of these exciting technologies. And now I'll turn it back to Vladislav, who's going to tell us a little bit about our next webinar. Over to you, Vladislav.
Thank you so much, Diane, for leading the discussion today. It was very interesting. And thank you so much, all the panelists, for providing excellent examples of disruptive technologies being used in different applications. Of course, thank you all the participants who joined us today and asked so many questions. Some of them were answered during the course of our discussion. But I do hope that we will be able to address in details these topics related to data safety, data protections during our next webinar. That will be taking place in 2 weeks from now and will be focused on cybersecurity enhancements. Thank you so much. Thank you, everyone.
Thank you, everyone. Have a lovely day.